everyone, welcome to part 3 of chapter 18. Thus far in chapter 18, we've looked at how to calculate entropy and changes in entropy of our system, and we've also studied the laws of thermodynamics. Well, now we're going to take those concepts and we are going to apply them to a new one, which is Gibbs free energy. So from the relationships of the change in entropy of the universe that we've looked at before, we can derive that our temperature times the change in entropy of the universe is equal to the change in enthalpy of our system, right? That's whether it's exothermic or endothermic, minus our temperature times our change in entropy of our system. So the entropy of our universe is being affected by the change in enthalpy of the system, because remember, that's affecting the entropy of the surroundings, and then minus the temperature times the change in entropy of our system, because remember, entropy is temperature dependent. Okay, so now we're going to look at Gibbs free energy, and Gibbs free energy is the maximum amount of work energy that can be released to the surroundings by a system when it's at constant temperature and pressure. The Gibbs free energy is often called chemical potential, because it's similar to how we store energy in a mechanical system, like when we have potential energy that we looked at before in a previous lecture with the guy that was pulling the rope, right, with the weight, and he was storing energy there. This is kind of the same thing. So Gibbs free energy is stored chemical potential. And so our equation of the day here is delta G of our system is equal to delta H of our systems minus T times delta S. Okay, the reason that this equation is so cool is that now we don't need any of, change in entropy of the universe or of the surroundings, right? This is all about the system. So now if we know pieces of information about our system, we can use that to calculate the other pieces. And so the change in Gibbs free energy, again, for a process occurring at constant temperature and pressure, is going to be proportional to the negative of delta S of the universe. Okay, so this is as our change in entropy of the universe is decreasing, our Gibbs free energy is increasing. Okay, they're always going to be opposite signed. So we know that our change in entropy of the universe is the thing that determines whether or not something is spontaneous, right? It's not the change in entropy of our system or the surroundings, right? But when we add them together, we're going to look at the change in entropy of the universe. But now we don't need to look at the universe. We're going to look at delta G of our system. So because of the relationship with the whole negative thing, right, if the change in entropy of our universe, we want that to be positive, so now we would like delta G to be negative. So things are positive, things are spontaneous, our reactions or our processes are spontaneous when our change in entropy of the universe is positive, or if our change in Gibbs free energy is negative. Either way. So if we think about a reaction, right, we could start with, completely reactants or completely products, but we know that the reaction spontaneously for a reversible reaction is going to shift the opposite way, right? Like if we have all reactants, we know it has to go to the right. And if we have all products, then it has to go to the left. Okay, that's because our reactants and our products both have a lot of free energy if we look at this diagram, okay? And so chemical systems tend toward lower Gibbs free energy or lower chemical potential, just like we have mechanical systems that will tend toward lower potential energy. Like the guy holding the weight again, right? If he lets go, that weight comes crashing to the ground. Here, if we, react our system or we allow it to go, it will form products or form reactants, right? It will start to, it will shift the opposite way of what we have. Okay, so we could try to get to equilibrium. And these are both spontaneous directions because we're trying to get to our equilibrium mixture. Okay, so you can see how we're going to start pulling in some of the other chapters here, right? We've got equilibrium going on. So again, a process will be spontaneous when delta G is negative. So again, now we can, look at just our system to figure out whether it's spontaneous or not, which is really nifty. So here's when delta G will be negative. So just looking at a mathematical relationship in our equation, if delta H is negative and delta S is positive, right, then we'll have a negative here, and we have minus T times a positive. That will make this whole thing negative essentially, right? Because we've got a positive times, this negative here. So it'll be a negative minus more stuff. And so delta G will always be negative. So it will be spontaneous at all temperatures if delta H is negative and delta S is positive. If we have a really big negative delta H and we have a fairly small delta S, but now it's negative, right? These two negatives will cancel out and that'll be a positive. But if delta H is still really large, then we can still have a negative delta G of our system, okay? So this will, if it's negative, and negative, if they're both negative, that will be spontaneous at really low temperatures because we want this second piece to be small compared to the delta H of our system. And if they're both positive, we want the opposite to be true, right? Because if we have a positive here and we're trying to make, delta G negative, then if this is positive, or if our delta S is positive, we want this to be really large so that this negative will, make our whole thing negative, essentially. And if they're both positive, then, not if they're both positive. If delta H is positive and delta S is negative, then there is no way that this will ever come out negative, right? If this is positive and we have a negative here, and so a negative times a negative makes this whole thing positive, then delta G will always be positive, which means it will never be spontaneous at any temperature. Okay, and if you, think about this in terms of what those letters mean, right? Delta H, we want that to be negative, right? We want that to be exothermic. And we want delta S to be positive. We want it to be increasing in randomness, in disorder, right? That's how we get these spontaneous systems. That's how we get this negative delta G. Okay, so if we think about this in terms of, logic, like we've been talking about previously, then that makes sense, right? Like this one, if delta H, our enthalpy, if that's positive, that means it's endothermic. And if delta S is negative, that means our system is becoming more ordered. Okay, so if it's endothermic and becoming more ordered, we are decreasing the entropy of our surroundings, we are decreasing the entropy of our system, and there's no way that the entropy of the universe can increase from that. Okay, so all of these mathematical relationships still relate back to the concepts we've talked about before. This bit at the bottom is important. When delta G is equal to 0, the reaction is at equilibrium. And this will be really useful for finding the temperatures at which phase changes occur. So I would make yourself a note that that's going to be really, really useful for those types of problems. Okay, so let's look at this again, just kind of qualitatively. So if delta H is negative and T delta S ends up being positive, then our value of delta G will always be negative and it will always be spontaneous. If the opposite is true, if we have a really, positive delta H, a negative T delta S, then we're always going to get a positive delta G, which means it will never ever be spontaneous. Because remember, we want delta G to be negative. If the signs are the same though, right, if they're both negative or both positive, then you need to do math. Okay, you need to figure out which one of these terms, whether it's delta H or T delta S, which one of those terms will be bigger and dictate the sign on delta G. Okay, if they're both negative, then it will be spontaneous at low temperature, and if they're both positive, then it will be spontaneous at high temperature. But I wouldn't bother memorizing that. I would just look at it mathematically because I try to minimize the number of things that I have to memorize because there is a lot going on. Okay, so here's just a couple examples. So I wanted to show you the last two, okay? So when we have water going from liquid to solid, okay, we know that our system is losing heat, right? Because it's cooling down. So that will be a negative delta H, which we're seeing here, and it's becoming more ordered, okay? So that will be a negative delta S. Okay, so if they're both negative, the only time it happens, right, where we get from liquid to solid, we know that it's only going to happen at low temperatures. Okay, it is not going to happen at like 100 degrees Celsius, right? You would think it's weird. If your liquid water froze into solid at 100 degrees Celsius, you would think that's odd, right? And that's a good example of when they're both negative. Okay, and then when they're both positive, we can think of it from liquid to gas, right? We are, that's endothermic reaction. We are taking in heat to change phase. So that's why we're getting a positive here. We are increasing in randomness and disorder because we're going from a liquid to a gas. So that's a positive. And we know that going from a liquid to a gas happens at 100 degrees Celsius. So that happens at a high temperature. That's when it's spontaneous. And it would not be spontaneous, right, at a low temperature. You would think it's weird. Again, if your water started to boil at, even room temperature, you would think that's a bit bizarre. So those are the ones that I would remember if you're looking for examples to remember for when they're both negative or both positive. Otherwise, you can use that mathematical relationship and always kind of reason it out. Okay, so I want you to do this practice problem. So which statement is true regarding the sublimation of dry ice, so solid carbon dioxide? And if you're not familiar with solid carbon dioxide, right, dry ice, it's cool. You just, set it on your lab bench or wherever you have it, or you can put it in water, which is really cool. And it goes directly from a solid to a gas. It skips the liquid phase. It's really awesome, especially for like Halloween parties and things like that. So I want you to figure out which of these is true. Okay, so go ahead, pause, think about what it means. Like, what does it mean when delta H is positive or negative? And what does it mean when delta S is positive or negative? And how is that affecting our delta G? Okay, so go ahead, pause here and see if you can reason it out. All right, let's go over this. So the first thing let's talk about delta H. So it's going from a solid to a gas. And to go from a solid to a gas, that needs to take in energy, right? We need to take in enough energy to make that phase change. So that means that delta S will be positive because it's absorbing heat. So can't be 2, can't be 3. And then it's going from a solid to a gas, so that means we are increasing in disorder, right? That means that delta S is positive, so can't be 4. So even if you only got that far, you should come up with our answer is number 1. But when we put in a positive here and a positive here, right, that means that it will be not spontaneous when this term is small, because that means our delta H will take over and will make our delta G positive. We need this term to be really big so that the negative here takes over the positive on the delta H. So that means that it will be spontaneous at high temperatures. Okay, so that's how you would reason that out. Let's do some math now. So we have our conversion of carbon tetrachloride to carbon and to chlorine gas. We have a delta H value and a delta S value. And I want you to we're going to calculate delta G and then figure out if the reaction is spontaneous or not. So we have a delta H, we have a delta S, and we have a temperature. So we are really set up to use that equation. So here we go. We have delta G is equal to delta H minus T delta S. And so we can just plug things in here. So we have 95.7 kilojoules for our delta H, and then we have 142.2 joules per kilogram at 25 degrees Celsius. Make sure you always change your temperatures to Kelvin. And the other thing that you need to note is that the signs of, the units of delta H and delta S don't match. We have kilojoules and we have joules. Well, joules per Kelvin, right? But we have kilojoules and joules. So those don't match. The units that we typically use for delta G are kilojoules per mole. So I'm going to go ahead and change my delta S into kilojoules per Kelvin so that my answer for delta G comes out in kilojoules or kilojoules per mole. If, you could totally do it the opposite way. You could change delta H into joules and do all your math that way. You just end up with really big numbers, and usually at the end, I'll ask you for the answer in kilojoules anyways, so I would save yourself a step and just convert delta S to kilojoules. So we can go ahead and math this out, and we get that delta G is 53.3 kilojoules. And if we, look at what this means, right, delta G is positive. That means this reaction is not spontaneous at this temperature. So what needs to happen, right, is we need to increase the temperature to make this term bigger so that our delta G will end up negative, because we can't affect this delta H. There's nothing we can do about that. It's always going to be positive. The only thing we can change is we can start to increase the temperature to make that term larger. All right, I would like you to try one. So go ahead and pause here and try this out. Calculate delta G and figure out if the reaction is spontaneous or not. All right, let's go over this. So, calculating delta G. Here we are, there's our equation, and we just kind of plug numbers in first. So we have our negative delta H value, and then we change our temperature to Kelvin, and then we'll change our entropy value into kilojoules per Kelvin so that all of our units match. And then you can just go ahead and math that out. And we get that we are having a negative delta G, which is great. That means that our reaction is spontaneous at this temperature, which is cool. So thinking about this, how we were thinking about the last one, right? We have a negative delta H value, and then we have a negative delta S, which is making this term positive. Okay, and so this will only be spontaneous at low temperatures. If the T delta S term gets too big, then that positive is going to take over and make delta G positive. All right, let's try another type of problem. So this one says a key step in the production of sulfuric acid is the oxidation of sulfur dioxide to sulfur trioxide. And so we have a delta G value, a delta H, and a delta S. And the first thing we're going to do is use the data to decide if the reaction is spontaneous at 25 degrees Celsius and predict how our change in Gibbs free energy will change with an increase in temperature. And then we're going to assume that our delta H and our delta S are constant with increasing temperature, so no phase change is going to happen. That would affect both delta H and delta S, right? Because we would need to have our enthalpy of, say, vaporization, and we'd get a big change in entropy for a phase change. And we want to know, is the reaction spontaneous at 900 degrees Celsius? So let's go through this. So if we look, delta G is negative here, right? That was given to us. So delta G is negative, so the reaction's spontaneous. That was awesome. Easy, right? No math needed. And so it asks, predict how delta G will change with increasing temperature. So we know our equation is delta G is equal to delta H minus T delta S. Okay, our delta H is negative and our delta S is negative, which is making this term positive, right? And so if we look, right, with delta S being negative, which makes that, negative T delta S positive, the term will become more positive at higher temperature, because as we get higher temperatures, that will make this term bigger, which will take over the negative delta H. So as we increase our temperature, delta G will become less negative, the reaction will be less spontaneous, and so on. And so then we can go ahead and calculate that last bit, right? If we assume delta H and delta S are constant, then we can just go ahead and plug those in. There's our delta H and delta S, and then we'll just use a different temperature. So we have 900 plus 273, and we'll plug that in. And then we can calculate our delta G value at that temperature. And just like we just said, at higher temperatures, right, that this term is going to become bigger, and if it becomes big enough, it will cause delta G to be positive. So that's what happened here, which is great. Our prediction was true. So delta G is greater than 0, so the reaction is not spontaneous at 900 degrees Celsius. Okay, so we've seen that our temperature has a big effect on reaction spontaneity, right? Especially if our signs don't match, or if our signs do match. If our signs don't match, then our reaction will either be spontaneous always or not spontaneous ever. So if we have a negative delta H and a positive delta S, then delta G will always come out negative. But if we have a positive delta H and a negative delta S, then our delta G will always come out positive. Okay, so if it's negative, it's always going to be spontaneous. If it's positive, it's never going to be spontaneous. Okay, and again, I wouldn't memorize these. I would just, look at it mathematically. But of course, if you're up for memorizing, you knock yourself out. But so the part that's different, right, is if the signs match. So if they're both positive or they're both negative. If they're both positive, then we need this term to be bigger, right? Because that negative here, we need that term to be really large to make our delta G negative. That means we need to have an increasing temperature. And then if they're both negative, then we want our delta H to be bigger. because this, that negative will cancel out this negative and it won't make it positive. So we need it to be really exothermic. So we need T to be small so that our delta H term is larger. Okay. All right, so now a different type of problem. Here we have the reaction of carbon tetrachloride to carbon and chlorine, again, that we were looking at earlier. And I want us to calculate the minimum temperature at which the reaction will be spontaneous. Okay, so you'll notice we don't have a delta G value. And so if you're, thinking about this, you're like, all right, well, we have delta G equals delta H minus T delta S. I don't have enough information. I'm missing two variables, right? I can't calculate a temperature. I don't have delta G. Okay, but the key here is delta G has to be negative in order for the reaction to be spontaneous. So we are going to, instead of putting delta G equals all of this, we are going to put that it's less than 0 because we just want it to be negative. So we can plug things in now because, again, we're solving for this, just less than 0. So we plug in our delta H value, and we have our T times our delta S. Again, make sure to always convert your delta S to match your units, and then you can solve. So we'll add our, our T term to both sides, okay, so that we can just move things around, and then we'll divide both sides by 0.1422, and we can get our T value. Okay, and again, this is going to come out in Kelvin. So here, the temperature has to be greater than 673 Kelvin in order for the reaction to be spontaneous. So I just want to note really quick here when we're doing this and we're dividing, if you divide by a positive number, then this, your equality, your like greater than less than, doesn't move, doesn't switch. If you divide by a negative number, like say that this was negative, right here, it's not, but say it was. If it was negative, then at this last bit, the sign would switch, okay? So if you divide by a negative, you have to flip it, okay? So that's my hint to you moving forward, because that's a common problem that people forget from when they've taken math. So let's go ahead and practice one. So I want you to pause here, try this problem out, and then come back when you're ready to see the answer. All right, let's go over this. So we have the reduction of copper oxide. It's non-spontaneous, and I want to know the temperature at which the reaction becomes spontaneous. So again, we know that delta G has to be negative in order for the reaction to be spontaneous. So we're going to use that delta G is less than 0 again. So we can plug in all our numbers, and then we will add, that to both sides, and then we will divide by that. And so then you get your answer. Pretty straightforward. Temperature has to be higher than 352 Kelvin in order for the reaction to be spontaneous. All right, so we've looked at one way to calculate delta G, right, which is using, that equation. There are actually a couple other ways to calculate delta G. So we can use that Gibbs equation if we're at constant temperature. We can also use the standard states, right? The standard free energy of formation of the components. And this equation should look very familiar. We have used this for delta H. We've used this for delta S. We can also use it for delta G. Okay, and so our delta G naught of the reaction, right, our standard change in Gibbs free energy of our reaction is going to be the Gibbs free energy of formation of the products minus the Gibbs formation of free energy of the reactants. And these will be values that you can look at in the table. It's a table in the back of your book, so you're not going to need to memorize these. You're just going to need to know how to use them. But again, it's the same thing we've been doing kind of over and over and over again. So we have the standard free energies of formation. Again, it's going to be on a table in the back of your book, and it's the change in free energy when 1 mole of the compound forms from its constituent elements in their standard states. Okay, so whenever we're forming some kind of compound, right, like carbon monoxide, carbon dioxide, etc. If we have, if we're, forming an element, then we're not going to have any Gibbs free energy for that. We're just going to say that just kind of exists. Right, so those will be 0, kind of like our change in enthalpy. The only one that's not 0 for these pure elements is going to be our entropy, because if you recall, they have more entropy than a perfect crystal at 0 Kelvin. That's how we were defining that. So back to this though, they do not have a Gibbs free energy of formation. So let's go ahead and try this. So here's a reaction. We've got some Gibbs free energy of formation, and then we are going to use that equation to calculate it up. So here we are. There's our equation. So we're always going to do products minus the reactants, and remember these N values, those are the coefficients in front of, whatever it is. So here it is. So we have carbon dioxide, right? There's just one of those. We have 2 waters, so we put a 2 here. We have 4 ozones, so there we go. And then we have 1 methane and 8 oxygens. Okay, so then we can go through and plug in the values from the table that we see over there. And you just go plug them in for whichever ones they are and then add them up. The only thing people ever do exciting here is they might drop a negative or so. But usually this is pretty straightforward because we've done a lot of problems like this already. So why don't you go ahead and try it out? So here's an equation. Here's some, different kind of problem. My apologies. I don't have a practice problem for you there because we've done so many already. This is the other way that it can show up. My apologies. We have, instead of giving us delta G values, I've now given you delta H values and delta S values, but I want you to calculate our change in free energy of this problem. Okay, so the way that we are going to do that is we are going to use that relationship that we were just looking at for delta G, where it was the products minus reactants, and we know that we can use that for delta H. We've done that a bunch, right? Products minus reactants. And we just learned in the last lecture that we can do that for entropy, right? Products minus reactants. So we can use that from delta H and S to find those, and then we can plug it into our Gibbs equation to find delta G. So here's how that looks. So we can first use that for our change in enthalpy of the reaction. So we'll go through and again, products minus reactants. So 2 times our hydrogen peroxide minus our 2 times water plus our oxygen. Okay, so there they are. And so you just kind of add those up, right? Remember, delta H of our oxygen, right, which is a pure element, that's going to be 0. We'll do the same thing for our change in entropy, but again, change in entropy now is not 0 for O2 because it is not a perfect crystal at 0 Kelvin, so we do have a number there for that. So we can calculate delta H and delta S from these tables of data, and then we can use our Gibbs equation and we can plug those values in order to calculate delta G. Okay, it said it was at 298 Kelvin up here. Again, just make sure that you're always converting your change in entropy value into kilojoules so that you can use it in your equation. So there you are. All right, so now we can learn yet another way to calculate delta G, and this is going to be related to Hess's law, which we learned about in Chem 1. So if a reaction can be expressed as a series of reactions, right? So like an overall reaction can be expressed as a series of reactions, right? Like a stepwise reaction, like a mechanism. Then we can add up the delta G values of the individual reactions to get the total delta G for that overall reaction. And this is because delta G is a state function. That's how we were also able to do that products minus reactants in that last example. If the reaction is reversed, right, so when we're doing these Hess's laws and adding together reactions, if we reverse our reactions, if we have to flip it, then the sign of delta G will reverse. So if it was positive, it becomes negative because we've turned the equation around. Essentially that means if it was spontaneous one way, right, then the reverse reaction is not spontaneous. So that makes sense. If we multiply our equation by a number, then we need to make sure to multiply delta G by that same value because delta G is an extensive value, right? It matters how much of it you have. So if we multiply all of our reactants by a number, say we multiply everything by 2, then we're also going to multiply delta G by 2. So let's go ahead and look at a problem. So this one says, find our change in Gibbs free energy for the following reaction using the given equation. So we have diamond changing to graphite, which we've talked about before, that diamond will spontaneously turn into graphite. We know that, you've learned that, so make sure the delta G at the end is negative, right? Because we've talked about that already. We should know that that one is a spontaneous process. But let's go ahead and look at how to manipulate these equations. So if we look, so diamond here, our carbon diamond is on the left, and we have carbon on the left here as a diamond. So that's already in the right place, and we only have one of them up here. We only have one of them up here. So that means that this reaction is already going the right way. We have the right amount of it. I'm just going to write it down again. If we look at the second reaction here, we have that graphite, right, is on the left, but we need graphite to be on the right to match our overall equation. So that means this reaction needs to be flipped. We only have one of it here and we have one of it here, so we have the right number, right? We don't need to multiply our reaction by anything. We just need to flip it around. So again, when we flip it, right, this was negative 394 and this became positive 394. So we flipped the sign. And then we can add together our reactions. So our oxygens will cancel out, our carbon dioxides will cancel out, and we can add our reactions straight down, and we see that our diamond is turning into graphite. And when we do this, we're just going to add together our delta G values, and we will get negative 3 kilojoules. Okay. Again, like I said earlier, we needed to make sure that delta G was negative because we know this is a spontaneous process. As you can see, it's got a fairly low value of delta G, which means it's not moving very quickly. It's not very spontaneous, but it is a spontaneous process. So we can use this whole, Gibbs free energy relationship, right, where we add together these reactions to do what's called coupled reactions. And so we can make a process that's non-spontaneous, we can make it be spontaneous by coupling it with another process that is really, really, really spontaneous. So essentially, if we, have one reaction that's not spontaneous, we have another one that has a really large value of Gibbs free energy, a change in Gibbs free energy, we can use that, kind of chemical potential to fuel the other reaction to go, is kind of how you can think about it. So here is an example. So we have this series of reaction is used to generate hydrogen gas. Okay, if we look, if we were trying to make hydrogen gas, say for fuel cells, which is a source of energy, the production of hydrogen gas from water is not spontaneous. This is not effective. And so if we were to use hydrogen as a fuel, we would need to get hydrogen first, and if we needed to go through and split water to get hydrogen, we're going to use more energy in producing our hydrogen than we would get out of it for using hydrogen as a fuel, which would not be effective or useful or anything. So we need to make this process spontaneous. So we can couple it with a really spontaneous process, like when we have carbon monoxide being oxidized to carbon dioxide. And this is very spontaneous. Okay, so as you can see, our second reaction is more spontaneous than the first reaction is non-spontaneous, essentially. And so if we can combine them together, right, we can use the oxygen produced in this reaction to make, as the, oxidation source for our carbon monoxide to turn into carbon dioxide. So this reaction, the second reaction, will essentially drive the first reaction to continue making more hydrogen. Because when we add these together, we get that the overall reaction is spontaneous. So this is coupled reactions, okay, where we can put two reactions together essentially, where one of, something that's being produced in that first reaction, like an intermediate, is going to be used up in the second reaction, but the whole purpose of it here is to make the overall reaction negative so that that reaction that we're wanting to make spontaneous now is. Okay. So here is, again, a coupled reaction, right? or a tripled reaction. I don't really know if that's a term, but we have all of these reactions coming together to give us the overall reaction. And so we're going to use that to calculate the Gibbs free energy. So let's go through and look at this. So I always kind of start left to right. When we have, let's look at the first one first. Here we have C3H8. That's propane. Okay, and so here propane is on the left and we want it to be on the right. We have the right number of propanes, but it's in the wrong place. So we're going to go ahead and flip that reaction. Okay, now let's go to the next one. So we have carbon here and we have 3 carbons here. Okay, so we have carbon is on the right side, but we don't have enough of them. And so we need to multiply this whole reaction by 3 so that we can add it with the other ones. Remember, when you do that, you're also going to multiply this Gibbs free energy by 3. And then let's look at hydrogen here. Hydrogen, we have it in the right spot. It's on the right-hand side, but we don't have enough of it. We only have 2, and we need to have 4. So we're going to multiply that whole reaction by 2, and we'll get that. Okay, so a lot of people ask me, well, why didn't I pick, maybe the oxygens or the carbon dioxides or maybe the waters, right? Those don't show up in this overall reaction. So it's really hard for us to base, if we're going to multiply it by something or flip it or what we're going to do. It's really hard to base our decisions on those molecules because they don't show up in our overall reaction, so they're not giving us a direction of what to do. So I would pick molecules that only show up in one place. Like this is the only place we see propane, and this is the only place we see propane. So that tells us what we need to do with the propane to put it in the right spot. Almost similar to the carbon and the hydrogen, right? It doesn't help us, if I was just looking at oxygen, there's no oxygen, so it doesn't help us to figure out, what to do with that. All right, so now we can add together all of our reactions, and we're going to make sure everything cancels out. Right, so we have 3 carbon dioxides on each side, got 4 waters, we have 5 oxygens, 2 plus 3 gives us 5, and then we are just left with what's in the overall reaction. So we can add that straight down, and we're going to do the same thing with our delta G's. We will just add them straight down. So this is giving us a negative delta G for the overall reaction. All right, I want you to try one of these. Make sure you're not rusty on this Hess's law type problem. So go ahead, pause here. Try this out, and then come back when you're ready to see the answers. All right, let's go over this. So here we are. We've got our 2 different reactions, and we need to put them together to equal the overall reaction. So for the first one, I would base this off of hydrogen peroxide, right? I know when you're looking at this, you can see that oxygen is in our overall reaction, but oxygen also shows up in this reaction too. So that may not help us because we can't really figure out what to do with our oxygen because it's in multiple places. So we would look at hydrogen peroxide here. It's on the right side, right? It's in the products in both of them, but we don't have enough of them. So we need to multiply this whole reaction by 2 in order to get our delta G value. And then looking at the second problem, right, now I would look at water, right? Water shows up here, and that's the only place, and it also shows up here. We have the right numbers of water, but it's on the wrong side. So we need to flip this reaction in order to make it match. So when we do that, remember, we're going to flip the sign of our delta G. So now everything is in the right place. We can go ahead and make sure everything cancels out. 2 hydrogens cancels 2 hydrogens. We have 2 oxygens on the left and 1 oxygen on the right. So those will cancel partially to give us 1 oxygen left over on the reactant side. And then when we add together our delta G's, we can, calculate our value. And that's the end of our slides for today. We talked a lot about Gibbs free energy and what it means when, the sign of delta H and the sign of delta S, how that affects our Gibbs free energy. And we looked at what does it mean when Gibbs free energy is negative or positive. We looked at a lot of different ways to calculate Gibbs free energy. We looked at using that Gibbs equation, right? That delta G equals delta H minus T delta S. We also used the relationship where we did the products minus the reactants. And then we looked at using, kind of like a Hess's law to calculate the delta G of reactions that are coupled, right? When we can add them together. So lots of different ways to calculate delta G and learn about Gibbs free energy. We're going to use this information more in the next lecture to look at different sets of equilibrium. What happens when it's not at a standard set of conditions or when it's not at equilibrium? How can we calculate the Gibbs free energy for those instances? So make sure you are working through those lecture worksheet problems so you build a solid foundation on how to calculate Gibbs free energy and understand what it means before moving on to the next lecture because it will help you out a lot. As always, if you have any questions, please send them my way. I am more than happy to help. But otherwise, I will talk to you guys next time.